Okay, guys, I'm back with another video. I have a feeling that Unit 2 is within this week, probably. So this one is from October 2025, so it's very recent, okay? I mean, in my channel, you will find the very recent one from January 2026, but this is very recent as well. And again, this is Saturday. I'm in my sister's office, and at 9 I have something else to do. It's a Saturday. So I will try to go over this kind of fast, but I will not cut down on quality. Okay, I will try. So let's dive in. Again, the general thing I always say, and you probably know it if you have watched many of my videos, guys. Spend about a minute per mark. So if a question awards 10 marks, you should approximately devote 10 minutes on it. Okay. If something doesn't occur immediately, skip it, solve problems that you know, and then come back later, and so on. And for the multiple choice section, it is often the case that you can eliminate all wrong answers and find the correct one, even if you don't know the correct one from the beginning. Okay, so let's dive in. First question, the graph shows how current I varies with potential difference V for an electrical component. Which of the following components will give this graph? It cannot be a diode because we'll have a sharp rise in the current at some voltage. A filament lamp is the perfect candidate. Okay, I mean, you see how as the voltage increases, the current increases, but not forever. I mean, at some point it plateaus. So just like it happens with filament lamps. But let's read the other answers. A resistor will be a straight line, and a thermistor, as the temperature increases, let me think, we will see something else, not this one. So B is the correct answer, okay? So let's move on. Now it bothers me, the thermistor would be, we will have a lot of increase in the current as the voltage increases pretty much, because it will heat up, so it will be more conduction electrons will make it in the valence band of that material, so we'll have a lot of current. So yeah, D is wrong as well. So let's go to number 2. The diagram represents a longitudinal wave. Which of the following is the wavelength for the wave, something like that. So we can do this like this. You can see that this wave has 4 compressions, right? So we have compression, 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 and compression. So the compression is where the lines come really close together, because in longitudinal waves, particles oscillate in the longitudinal direction. Okay, so at some points they have compressions, and then you have rarefactions. Let's mark them in red. So that's a rarefaction, another rarefaction, and another rarefaction. Excuse me. So compressions, if you plot this as a wave, okay, it would look like this. Okay, I will try to draw it first, and then I will explain what I did. Okay, so it will look like this. Wait, I don't have enough space, so I'm gonna cut this. Oops, cut. Let's go to a clean page, and let's do paste. Sorry for for wasting your time. So okay, it would look like, okay, we have that and that, and I need 2 more peaks pretty much, so something like this. Okay, okay, so that's the compression. Wait, let's use the same color. I used orange, right? So that's a compression, that's a compression. Wait, I need more, and that's a compression. And okay, you need 1 more pretty much. So 1 lambda, 2 lambdas, and we actually need to move this again. So let's move it over there. Okay, so let's move it there, so I have space. Sorry about that. And we'll need that. Okay, so we have 4 compressions and we have three rarefactions. Okay, the rarefactions are the minima, and the compressions are the maxima. So how many wavelengths do we have here? So we have 1, 2, 3 wavelengths. So 3 lambda is 6 meters. So lambda is just 2 meters. Okay, so the answer is A. I hope this makes sense, but it can get confusing when you see longitudinal waves. So I wanted to help you have a picture of what's happening in your heads. Okay, let's move to the next question. Okay, question 3. The diagram shows the trace of a sound wave on an oscilloscope. One horizontal division represents a time of 5 milliseconds. Which of the following expressions gives the frequency of the sound wave in hertz? Okay, so again, we will use, we'll find the wavelength going from peak to peak. So one peak, and that's the second peak. And there are 4 squares in between this. So the period is going to be 4 times 0.005, and this 0.005 is 5 milliseconds. So the frequency is going to be 1 over that. So 1 over 4 times 0.05, or answer D. Okay. And now question 4. An electron has a velocity of 2 times 10 to the 7 meters per second. Which of the following expressions gives the de Broglie wavelength? And I always say Prince de Broglie because he was an aristocrat. Okay, gives the de Broglie wavelength of the electron in meters. So lambda is h over p, is Prince de Broglie's formula. So h over m times v. So we need Planck's constant in the numerator, right? And then we need the mass of an electron, which is 9.11 times 10 to the negative 31 kilograms, times the velocity, which is 2 times 10 to the 7. And immediately we see that the correct answer is B, right? And I want to address here the thing I always say, I call it the lawyer's way, because lawyers usually arrive at the correct answer by eliminating all the wrong answers. Okay, so options C and D are erroneously wrong because you have the Planck constant in the denominator. So you're only left with A and B. And by inspection, you see that A and B are identical, except that in A, they use that mass. And that mass is the mass of, pause the video, and write in the comment section what kind of particle that is. Okay, assumed you wrote. So the answer is proton. Okay, so that will be the de Broglie wavelength of a proton or a neutron. I mean, they have almost the same mass. So yeah, I mean, you can eliminate A as well. So in this case, you can eliminate all the answers just by inspection, okay, without even writing the formula, I mean, okay. So let's go to question 5. 2 points on a wave have a phase difference of 25 degrees. Which of the following expressions gives the phase difference in radians? Okay, this one is easy. So we have degrees. So we somehow have to divide by degrees and multiply by radians. So I usually use pi, and 1 pi corresponds to 180 degrees. And by inspection, you see that none of these answers is that, but you can multiply by 2. So 25 degrees times 2 pi over 360 degrees. And immediately you arrive at option A. Okay. And by inspection, all the other options here are also wrong. I mean, if you inspect this, for example, B and D are totally wrong because you are dividing degrees with degrees. So you devise and dimensionless quantity, okay? But the quantity we want to devise has unit of radians. So in this case, only A and C are plausible answers. But C is wrong because pi is not 360 degrees. It's actually 180. So C is also wrong. So again, by elimination, you can find the answer. All right. 6. A bat is an animal that locates objects using a pulse echo technique. A bat emits a pulse of sound waves that travel to an object. The bat detects the reflected pulse 4 milliseconds later. The speed of sound is 340 meters per second. Which of the following expressions gives the distance in meters between the bud and the object? Okay, we're gonna use S is V over T, but we will have to divide by 2, right? Because the bud will send a pulse to the object, and then that pulse is gonna bounce and travel back, okay? So V is the speed of sound, of course, 340 times the time, 4 times 10 to the negative 3 over 2, which is option D, right? And again, in this example, you can again eliminate most answers just by inspection, okay? Okay, let's move on. Question 7. A string vibrates between two fixed points. The diagram shows the stationary wave formed on the string when the string vibrates with frequency f. The tension in the string is doubled. The frequency of vibration is adjusted until the same shape of standing wave forms on the string. Okay, I'm going to underline this. Okay, that's the key there. Okay, which of the following expressions gives the frequency f of the new standing wave? So what I underlined is the most important piece of information about this problem, because they tell you that they want the wavelength to be the same. Okay, so let's start by, let me use a clean page because I will need to write a few things. So the velocity is going to be the square root of the tension over the mass per unit length of this string. Okay, and the velocity of a wave is lambda times the frequency, and this should be equal to square root of t over mu. Okay, now when we double the tension, we will have a new wavelength times a new frequency being equal to 2t over mu, okay, because we use the same string. But as we said, this lambda prime is the same as before, so we will have lambda times f being equal to the square root of 2t over mu, okay. So we will have lambda times, sorry, it's going to be f prime, excuse me. So lambda times f prime is going to be the square root of 2 times lambda times the old frequency, okay. So lambda cancels, so f prime is simply the square root of 2 times the old frequency, okay. And that's the answer. So if we go back, this is option B, okay. This one is an example that you actually have to work out, because you cannot infer the right answer by inspection. So let's move on. Question 8. A student connects 5 identical 1.5 volt cells in parallel to form a battery. Each cell has an internal resistance of 1 ohms. Which row of the table gives the EMF and internal resistance of the battery? Okay, so the EMF, if we connect batteries in parallel, okay, we see that across the wire, so at these points that I mark with red, the voltage drop is still 1.5 volts, okay? To increase the voltage drop, you have to align them in series. So immediately we know that it's going to be option A or option B, okay? Now, what's the internal resistance? We simply we put these batteries in parallel, so 1 over R total is going to be equal to 5 times 1 over R, which is the resistance, the internal resistance of the batteries. This is 1 over R plus 1 over R, etc. Okay, so R total is going to be the internal resistance of one battery over 5, or 0.2 ohms. So the correct answer is A. Okay, and we can erase this one. Okay, this was question 8. So let's move on to the question number 9. Okay, question 9. The diagram shows the energy levels in an atom. This is a very strange atom. It doesn't exist in nature, as far as I am concerned. And I mean, I don't know of any elements that have such an integer energy level distribution, okay? So it's a made-up atom, okay? I think. I mean, I'm 99.99999% sure. Google it and let me know if I'm wrong, but I don't know of an atom that looks like that. Anyway, when the electron moves from n equals to 4 to the ground state, okay, a photon of frequency f is emitted. So we have this jump. Okay, that one. So h times this frequency is going to be pretty much 4 electron volts, because you go from -1 to -5. So the difference is 4 electron volts. Okay. Now, okay, which of the following photon frequencies could not be emitted by this atom? Okay, f over 8, to have a frequency of light of f over 8, we'll need h times f over 8 to be equal to 4 electron volts over 8 electron volts, which is 0.5 electron volts. So that's the wrong answer, okay, immediately. And why is that? Because in this atom, we can only have integer jumps because the energy is integer, right? So the only possibilities are, let's see, I mean, an electron might jump from 4 to 3, that's a change of 1 electron volt, or from n equals 4 to n equals 2 in this case, which is a jump of 3, or we can have the same electron from n equals to 4 to jump to, I mean, this is the one we just examined, that's a change of 4. Other possibilities include a jump from n equals to 3 to n equals to 2. That's again 2 electron volts. And then this jump is 3 electron volts, and so on and so forth. In short, this jump has to have an integer change of electron volts. Okay, so we cannot have half an EV. So that's impossible. So A is the correct answer. Let's move on. Question 10. The diagram shows a 4 ohms resistor connected to a cell of EMF 12 volts and internal resistance 2 ohms. Which of the following expressions gives the potential difference V across the internal resistance of the cell? Okay, so first of all, we need to find the total resistance, which is going to be 6 ohms. We just add them up. Therefore, the current in the circuit is going to be V over R, so 12 over 6. I don't write 2 because they have these weird fractions there, so I kept it as 12 over 6, okay? So the voltage across R, the internal resistance, is going to be I times R, so 12 over 6 times 2, or 12 times 2 over 6, which is option D. Okay, so this was section A. Straightforward for the most part, I think. But if something wasn't clear enough, please let me know in the comments. And also, guys, please subscribe. I say it in most of my videos. 85% of the people who watch these videos are not subscribed. This is really sad. It doesn't cost anything. So, and yeah, let's move on. Okay, section B. Question 11. A wire of cross-sectional area 2.8 times 10 to the minus 6 square meters is connected in a circuit. There is a current of 2.5 amps in the wire. Calculate the drift velocity of the electrons in the wire, and they give you the number of charge carriers per unit volume. Okay, so the current is NQVA. Okay, so the number of charge carriers times their charge times the drift velocity times the cross-sectional area. So V is I over NQA. Okay, so that's 2.5, and then we have 8.5 times 10 to the 28. Actually, let me use units as well. So I say it in most of my videos that I prefer to arrive to an algebraic expression that before plugging in numbers. So in this case, it's I over NQA. And then when I plug in numbers, I put all the numbers to the left. So numbers are to the left, and to the right I put all the units, okay? So I hope this makes sense. So in the numerator we will have amps, and 1 amp is 1 coulomb per second, okay? And then in the denominator we have charge carriers, which have units meters to the -3, so meters cubed goes in the numerator, okay? Times charge, 1.6 times 10 to the -19. So we have coulombs. And then we're gonna run out of space, sadly, okay. And then we have, actually, let me try to move this a little bit. So this part goes there, okay. I will need the eraser, okay. Sorry about that. And then 2.8 times 10 to the -6, and then we have square meters. So I want to show you that coulombs cancel, meter square cancelled, and we have just meters. So we are left with meters per second. Okay, I just wanted you to see that you can work with units the same way you work with numbers. Okay, so the answer is 6.57 times 10 to the -5 meters per second. Very slow. Okay, let's move on. Question 12. Coffee machine is connected across a 230 volts power supply. That's the voltage, sorry, that's the potential difference used in Cyprus as well, but I believe in the UK as well. Let me know in the comments. Let me know actually the potential that you have at your homes. So the heating element in the coffee machine has a resistance of 18 ohms. The coffee machine takes 38 seconds to heat enough water to make 1 cup of coffee. Calculate the energy transferred by the heating element in 38 seconds. Okay, so the power is given by V squared over R for this heating element, but power is energy over time, and this is equal to V squared over R. So energy is V squared over R times time, so 230 squared over 18 times 38 seconds, and this yields 111,678 joules. Okay, I think probably you should write something like 1.12 times 10 to the 5 joules. It looks better. So anyway, B, explain why the resistance of the heating element increases as its temperature increases. So electrons collide with lattice ions. And when we say lattice ions, metals internally look like this. So you have ions that do not really move, okay, compared to the electrons. And then you have free electrons flowing around, okay. As you increase the temperature of this material, these ions will start to vibrate. So this creates a larger surface area, if you will, for electrons to collide with these ions. So the resistance increases because electrons collide more. Okay, so that's the answer, but let's write it down. So I will write down what I just said. So higher T means higher lattice vibrations. Okay, higher lattice vibrations. And then this means more frequent collisions. So more frequent collisions occur. So we have a higher resistance. Okay, and this was question 12. I think there is nothing more to say. Let's move on to question number 13. A student determined the resistivity for a metal in the form of a wire. Okay, the student measured the resistance for different lengths of the wire. She plotted the graph shown, okay, resistance versus length. So we have a table here that shows the resistivity of some metals. So they have constant nichrome, I don't know that. and copper. Okay, deduce which of these materials the wire was made from, and they give you the diameter of wire. Okay, so the resistance is equal to the resistivity times length over cross-sectional area. Okay, which you can write as as rho over A times L. Okay, so the gradient is going to be equal to the resistivity times A if you plot if R versus L is plotted. Okay, so the resistivity is equal to the gradient times the cross-sectional area. Okay, and now the gradient is delta R over delta L. So we have to go back to the graph and pick 2 points. Any 2 points will do. I chose this one and this one for convenience. Excuse me. Okay, but you can pick any 2 points. So for those 2 points, we have delta R being equal to 10 minus 4. Okay, and this is ohms. And then in the denominator, we have 82 minus 26, and then we have to multiply by 10 to the minus 2 because that's in centimeters. Okay, so the gradient is actually 10.71 ohms per meter. Okay, so the resistivity is going to be the gradient times A. So let me write there that is equal to the gradient times pi d squared over 4, since they are giving us the diameter. So let's write things down, 10.71, and this is again ohms per meter, times pi times 0.24 times 10 to the negative 3, and this is squared, meter squared over 4. And the answer is 4.85 times 10 to the negative 7 ohms per meter, which means that it's constant time. Okay, very close to what we found. Okay, I hope this is clear. We're ready to move on to the next question. Okay, question 14. A student used a semicircular glass block to investigate the refraction of light. He directed a ray of light onto the glass block as shown. State why the ray of light does not refract as it enters the glass block. So they mean this part over there. Okay. And the reason is that the ray of light is aligned with the normal, right? So we can write that. So angle of incidence is 0, and then we can write that it's aligned with normal. So no refraction. Okay, so no refraction. Because if you use Snell's law, you will have n1 sines and then sine of 0, which is 0. Okay, so you will necessarily have this must be equal to n2 times sine of 0 as well. Okay, so that's the only way it can work. So both the incident and the refractive angles are 0. I'm going to write this in parentheses. You don't have to write that in a test. Okay. B, the glass has a refractive index of 1.5. The ray of light is refracted at the curved surface of the block. Calculate the angle of refraction. Okay, Snell's law, 1.5 times sine of 35 is equal to 1, because that's air, times sine of theta, the one that we're trying to find. So sine of theta is 0.86, and then theta is 59.36 degrees, which is what we expect when we go from an optically dense material to a less dense material. So we go from glass to air, so we expect the refracted light to bend away from the normal. Okay, so that's the answer. Let's move on. Part 2. Complete the diagram to show the path of the ray of light as it leaves the glass block. Okay, so Let's use red. So it's gonna go this way, bending away from the normal. Okay, so this will be the ray, and this angle is going to be 59 point. What did we find? 36, right? Yes, 59.36 degrees. Okay, this was problem 2. Let's turn the page. There is one more. Okay. The student moved the glass block so that the ray of light was incident on the curved surface at the critical angle C as shown below. Determine the distance x. They give you the refractive index of glass, which is 1.5, like before, of course, and the radius of the glass block as 45 millimeters. Okay, so there is an old theorem in geometry that I think you don't really need it, but if this is the tangent to the circle, this is going to be perpendicular to the tangent, so it passes through the center. So I'm trying to say that that's the center. Actually, let me use a dot to avoid confusion. So that's the center. So x is really r. So this distance x is r plus this distance that we will call L, okay? And then this is also r. Okay, I hope this makes sense. I mean, this is the geometry of the problem. Now let's find the critical angle. We have 1.5 times sine of the critical angle should be equal to 1, the index of refraction of air, times sine of 90 for total internal reflection. So that's 1. So the critical angle C is 41.81 degrees. And then we see immediately that x is r plus L, but the sine of the critical angle is equal to L over r. And if we combine these two, we find that x is r plus r sine of C. And if we do the calculations, we find 75 millimeters exactly. I mean, okay. So this was a nice problem, I think, because you end up with a round answer. Okay. This was question 14. We are ready to move on to the next one. Okay, question 15. The photograph shows a flame detector. The flame detector uses the photoelectric effect to detect the ultraviolet radiation from fires. I actually didn't know that, okay? I mean, I didn't know about this detector, to be honest, before solving this problem. Okay, there's a glass window there and a detection surface behind the glass window. Question A asks to explain how electrons are released in the photoelectric effect. So, one photon hits one electron. Okay, that's the first step. So the energy of the photon is h times the frequency. So energy is proportional to frequency. So some of this energy, some of the photon's energy is used to release one electron. To overcome the work function. Excuse me. Okay, so some of the photon's energy is used to overcome the work function. Okay, and then whatever energy is left from that operation is converted to kinetic energy of the electron. So whatever energy is left, whatever energy is left is used as kinetic energy of the electron. Okay, and the equation is h times the frequency of the photon is equal to the work function plus the maximum kinetic energy of the electron. Okay, let's move on. Part B. A fire emits photons of ultraviolet radiation with a wavelength of 380 nanometers. Show that the energy of each photon is about 5 times 10 to the negative 19 joules. Okay, so energy is h times frequency, or h times c over lambda, because lambda times F is C for all electromagnetic radiation, including light, radio waves, what else? Gamma rays, whatever. X-rays, okay? So we have 6.63 times 10 to the negative 34 times 3 times 10 to the 8 over 380 times 10 to the negative 9 meters. So this yields 5.2 times 10 to the negative 19 joules. Okay, part 2. Calculate the maximum kinetic energy of the released electrons in electron volts, and they give you the work function of the metal. Okay, so we have to solve the equation that we mentioned in our first answer. So H times F is the work function plus key E max, which means that key E, the kinetic energy max, is equal to HF minus the work function. So 5.2 times 10 to the negative 19, and then the work function is given, minus 2.2, and then 1 electron volt is 1.6 times 10 to the negative 19 joules, and this yields 1.71 times 10 to the negative 19 joules. And if we divide again by 1.6 times 10 to the negative 19, we will find that this is equal to 1.07 electron volt. Part 3, UV radiation with an intensity of 8,000 watts per square meters is incident on the detection surface. Excuse me. The detection surface has an area of 0.02 square meters. Determine the number of photons incident on the detection surface, each second. Okay, so the intensity is equal to the power over area. So power is the intensity, which is 8,000 watts per square meters, times 0.02 square meters, which yields 160 watts. Now, if we divide 160 watts, which is pretty much joules per second, right? I mean, watts are joules per second. If we divide that with the energy of one photon, which is 5.2 times 10 to the negative 19 joules, we will find the number of photons incident on the detection surface per second, okay? And this division gives you a very large number, 3.08 times 10 to the 20 photons per second. All right. There is a part C in this question. So in part C, they say that the detection surface is part of an electrical circuit. The released electrons cause a current in this circuit. Okay. The intensity of ultraviolet radiation incident on the detection surface increases. Explain how this will affect the current in the circuit. So more intensity means more photons per second, right? Okay. Now, more photons means more electrons released per second, okay? And then more electrons per second means greater current. Okay, so this was question 15. We're ready to move on to question number 16. Okay, question 16. A student directed light from a laser onto a diffraction grating as shown. A series of bright dots was formed on the screen. AI, that's the first question. The light from the laser is coherent. State what is meant by coherent light. So there is a constant phase difference. So constant phase difference between waves. Okay. Part 2, explain why a series of bright dots was formed on the screen. Okay, so the path difference has to be an integer number of, an integer multiple of wavelengths. So, okay, so the path difference has to be an integer multiple of lambda, pretty much, okay? So waves arrive in phase. So constructive superposition occurs. All right. B. The diffraction grating has a grating spacing d of 1.07 times 10 to the negative 6 meters. Calculate the angle between the central maximum and the first order maximum, and the wavelength of laser light is 532 nanometers. Okay, so we have to use d sine theta, because you will have a central maximum, and then the first maximum will be over there, so you just have to use we need to find that angle pretty much. Okay, so d sine theta should be an integer multiple of lambda with n equals to 1, since this is the first order, so sine theta is lambda over d, or 532 times 10 to the negative 9 over 107 times 10 to the minus 6, and this yields an angle theta of 29.81 degrees. Okay, part 2. The student observed first and second order maxima. Explain why it is not possible for a third order maximum to be produced. Okay, so sine theta, okay, this division I didn't wrote it earlier. So this is equal to 0.5 pretty much, okay? So you immediately see that since sine theta is an integer number multiplied by lambda over d, so in our case it's going to be n times 0.5, okay? So if n is equal to 3, then sine theta is going to be 1.5, which is larger than 1, so not possible. Okay, so you will never see a third order maximum. Okay, the student replaced the laser with a lamp that produced a narrow beam of white light. Describe the pattern that formed on the screen. So we will have a white dot in the middle. Okay, so we have a spectra on either side. Okay, and the violet would be close to the center, and red will be further from the center. And the reason is that sine theta is proportional to 1 over lambda, okay? So the smaller lambdas will be close to the center, whereas the larger lambdas are going to be away from the center. Okay. So this was question 16. I think we're ready to move on to the next one. Okay, question 17. Water in a water bath is heated using an electric heater. The heating circuit is switched on and off by the control circuit shown. The cell has negligible internal resistance. Okay, the thermistor is placed in the water. When the potential difference PD across the thermistor is above a certain value, the heating circuit is switched on. Explain how increasing the temperature of the water affects the potential difference across the thermistor. You should refer to conduction electrons in your answer. Higher temperature means electrons gain energy. Okay, so that's the first thing we can write. Then this means that more conduction electrons are released. Okay, so the thermistor's resistance decreases. Okay, so the thermistor now has a smaller fraction of the total resistance. So thermistor now has a smaller fraction of the total resistance. So a smaller fraction, so a smaller fraction of the 6 volts is dropped across the thermistor. Okay, I hope this makes sense. This is why it's called the negative temperature thermistor, because as the temperature increases, the resistance decreases, and this is because these are semiconducting materials. So if you increase the temperature, the resistance decreases, and also there are more electrons around to conduct electricity. Okay, let's move on. This was a long writing problem, by the way, okay, with an asterisk. I usually comment that in these types of questions that you have to provide evidence or responses to something. You have to write about 1 sentence per mark. So here we wrote 5, but I think it's plenty, okay? Let's move on. Part B, the heater will switch off when the potential difference across the thermistor is 0.9 volts. The water temperature should reach 65 degrees Celsius. The resistance of the thermistor at 65 degrees Celsius is 56 ohms. The resistance of the fixed resistor is 300 ohms. Deduce whether the heater will switch off when the water temperature reaches 65 degrees. Okay, let's find the total resistance. It's going to be 56 plus 300, so 356 ohms. Then the potential difference across the thermistor is going to be 6 times 56 over the total resistance, 356. I hope this is clear. If it's not clear, I can provide more explanations in the comment section, okay? So this yields 0.94 volts, but 0.94 volts is larger than 0.9 volts. So the thermistor stays on, actually. The thermistor stays on, okay? And that's the answer. Okay, let's move on to the next one, which is the last one, okay? This was shorter from what I have seen from past papers recently. Usually they have 20 questions, I mean. But anyway, okay, let's do it. Let's do this. A student directs unpolarized light through a polarizing filter. After passing through the polarizing filter, the light is plane polarized. Explain the difference between unpolarized light and plane polarized light. So in unpolarized light, you have oscillations in all directions. Okay, so the light will look like this. So you will have an oscillation in that direction and maybe an oscillation in the direction that is perpendicular to that, something like that. Okay, in polarized, so in plane polarized light, the oscillations are in one plane only. Okay, so and also that plane includes the direction of travel. So what we mean by that is that plane polarized, light will look like this. Okay, so this light travels in this direction. So you see that the oscillations are only in this plane that I just drew. Okay, I hope this makes sense. Whereas in the other light I drew, you have a plane like that, and it also includes a plane like this. So you see that it oscillates in many different planes pretty much. Okay, I hope this makes sense. If it doesn't, please Google it and find a better picture. I don't know how else to describe it. Okay. Part 2. The student rotates the polarizing filter. Explain why rotating the polarizing filter will not change the intensity of the light that passes through the filter. So the filter transmits, one plane at a time. okay? And polarized light has equal energy in all planes, okay? Rotating the filter selects a different plane, okay? But the same amount goes through. Okay, so rotating just polarizes the incident and polarized light into one plane. So it selects one plane, doesn't. So the intensity of radiation for that polarized plane will be the same irrespective of which is the plane of polarization. Okay, I hope this makes sense. Let's move to the next one. Okay, part B. The student arranges 3 polarizing filters in different orientations. The arrows in the diagram show the initial orientation of the plane of polarization of each filter. So we see that filter 1 and filter 2 are the same, have the same polarization, and filter 3 is perpendicular to the first two. Now the student rotates filter 2 by 45 degrees. The intensity of light that passes through filter 3 changes. Explain how rotating filter 2 by 45 degrees from its initial orientation affects the intensity of light passing through filter 3. Okay, so let's write down that initially filter 2 is aligned with filter 1, okay, and filter 3 is perpendicular to 2, okay. So zero light passes through 3, okay, because initially you have this polarization going through and then this, so we start with all polarizations, I mean in all possible planes. Then through filter 1 we have that polarization that remains the same after filter 2, but then filter 3 blocks that, okay, so there is nothing after filter 3, okay. But after rotating filter 2 by 45 degrees, it is no longer, so after rotating filter 2 by 45 degrees, it is no longer aligned with 1. So it is no longer, let's write perpendicular to 3 actually, perpendicular to 3, and of course not aligned with 1. Okay, so some light through filter 2, oops, what did I write there? So some light through filter 2 has component that passes through filter 3, okay? So intensity rises from 0. And let me try to explain. Okay, so the situation after the first filter is the same, but now after filter 2, we will have light that looks like this, okay? Because it will pass through, so that component of the light will pass through filter 2, and then through filter 3, part of this filter 2 is going to pass through, and we will have light that oscillates in this direction. And you can think of this as analyzing, if we take this light, we can analyze it into a component that looks like that and a component that looks like that. Or in other words, if we have light that is oscillating in this plane and a light that oscillates in that plane, we will get light that oscillates in 45 degrees. Okay, so this component will pass through filter 3. Okay, and that's the answer. Okay, this was unit 5, unit 2, excuse me, from October 2025. I was feeling really exhausted and I didn't work on past papers this week, but hopefully I will keep them coming as you also need them for your current exam period. I hope these videos are useful. Thank you so much for those of you who write comments, very encouraging comments under my videos. I hope this community to grow, include more viewers, and that eventually get monetized, because it's really hard to keep up without getting anything out of this. And I'm open to donations. I mean, I don't know. I mean, I put the link there, but nobody really sees it. Okay. I hope one day I make a living out of this or something like that. We'll see. Thank you guys for watching, and see you in the next one. Bye.